Motion is an essential element in video generation, and generating motion that aligns with physics and common sense is especially important. In this work, we present MotiMotion, a framework that produces realistic motion-controlled videos through visual reasoning. We can precisely control motion in videos using trajectories. However, user-provided trajectories are often sparse and only describe the primary motion. In real-world videos, motion usually involves not only a single moving object, but also interactions between objects and chains of events. A user trajectory can trigger new events or influence the surrounding environment. This reactive or secondary motion should also follow physics and common sense. Here are some examples where user trajectories trigger additional events. To model these events correctly, video generators need to understand physics, common sense, and more generally, knowledge about the world. In our experiments, we found that current video generators still struggle to model these dynamics reliably. To better align motion with physics and common sense, our key idea is to integrate an external knowledge provider, such as a vision language model, or VLM. The VLM predicts what may happen next and how objects should move, while the video generator produces videos based on these predictions. For example, if a user draws an upward trajectory to lift the thumb, the VLM predicts an additional downward trajectory, showing the fire being extinguished. Next, let's look at the method in more detail. Here is an overview of our pipeline. The framework consists of two stages, a reasoning stage and a generation stage. In the first stage, the VLM reasons about the input image, refines the prompt, and plans the motion. In the second stage, the video generator produces the final video according to this motion plan. To control motion, we place white Gaussian maps at the trajectory locations across frames on a black canvas. This creates a volume with the same shape as the video, so we can concatenate the video and the control volume. We will also show that our reasoning module can improve other motion-controlled approaches. In the reasoning stage, the VLM takes three inputs. First, the input image with trajectory visualizations, which helps the VLM understand the spatial relationships. Second, the trajectories represented as numerical coordinates, which provide a precise reference when the visualization is ambiguous. Third, the user prompt, which is optional because users may not always describe the motion explicitly, and the model should also infer motion directly from trajectories. Giving these inputs, the VLM is instructed to slightly refine the user trajectories to better match the visual context and to propose additional trajectories for secondary motion. Here are some examples of VLM predicted trajectories. Given a downward trajectory pressing the right side of the seesaw, the VLM predicts an upward trajectory on the left side. It also predicts a fixed point representing the fulcrum. Both the input and output are represented purely as text, and we use relative coordinates to avoid issues caused by resizing inside the VLM. Although the VLM can predict plausible motion, the predicted trajectories do not always align perfectly with image pixels. In practice, human trajectories are also imperfect. They are often simplified and overly smooth. These shifted or over-smoothed trajectories can introduce visual artifacts. To address this issue, we make the trajectory control elastic. We assume the video model has already learned natural motion patterns from large-scale training data. We assign a confidence score to each trajectory. With high confidence, the video generator closely follows the trajectory. With low confidence, the generator is allowed to improvise, correct errors, and enrich missing details when trajectories are imperfect. Technically, we scale the Gaussian maps to modulate control strength based on the confidence level. During training, we randomly augment and corrupt some trajectories, for example, by smoothing them to simulate imperfect user input. Next, we show the experiments and results. We first construct a benchmark of pre-event scenes. Each sample contains an image, trajectories, and a prompt. The benchmark covers diverse scenarios, including collisions, constraint changes, tool mechanisms, airflow, and common objects. Here are some examples of trajectories predicted by the VLM. Here is a comparison between MotiMotion and other approaches. Here is the ablation study for confidence-aware control. We set the user trajectories to high confidence and compare predicted trajectories with high versus low confidence. Low confidence control helps correct distortions and trajectory shifts, leading to more natural motion. In summary, we identify the challenge of modeling complex motion in motion-controlled video generation, and we integrate VLMs to leverage their reasoning capabilities. Specifically, we propose MotiMotion, a framework that uses VLMs to provide plausible semantic and motion control together with confidence modulation to further improve motion naturalness. We also introduce MotiBench, a benchmark for physical and causal reasoning, where MotiMotion is preferred over previous methods. Thank you for watching. Please check out our paper and project website for more details and results.